What if I told you that cleaning up the toxic air pollution in our most crowded cities could actually, like, accelerate global warming?
Right, in a short term, yeah.
Yeah, in the short term. I mean, today's deep dive is looking into what is basically a terrifying planetary catch-22.
It really is.
We're working from this really dense, but totally fascinating set of academic notes on something called the atmospheric aerosol loading planetary boundary. And our mission today, basically, is to figure out the hidden architecture of the air we're breathing right now. Like, we're going to map out how a hyperlocal smog cloud, scales up into an Earth system crisis.
Right.
And we're going to explore the incredibly daunting physics of why scrubbing our skies clean might actually rip away a dirty sunshade that's currently protecting us from the full force of climate change.
Yeah, it's a phenomenal set of notes, honestly, because it forces us to hold two completely contradictory environmental truths in our heads at the exact same time.
Right.
I mean, it completely shatters the usual assumption that all pollution just acts like carbon dioxide.
Okay, yes, let's unpack this, because that was the very first thing that jumped out at me. Usually when we talk about atmospheric pollution, we immediately picture CO2.
Exactly, yeah.
You look at a global graph, it's ticking upward, you measure it, and it's essentially the same math, whether you're in New York or, like, Antarctica. But based on the text, aerosols play by an entirely different set of rules. And just to be clear for everyone, when the notes say aerosols, they aren't talking about, deodorant cans or hairspray.
Far from it, yeah. I mean, we're talking about microscopic, solid, or liquid particles that are just suspended in the atmosphere.
Okay.
And the text categorizes them into several types. So you've got black carbon, sulfates, organic aerosols, mineral dust blowing off deserts, sea salt and smoke from wildfires or agricultural burning.
So it's a huge mix.
Yeah, a massive mix of entirely natural sources and heavily human-driven ones.
And to figure out how much of this stuff is actually up there, scientists use this metric called aerosol optical depth, or AOD.
Right.
And the notes have this analogy for AOD that I actually really love. It's like shining a flashlight into a fog bank.
Yes, I love that one too. It translates this highly abstract, dimensionless metric into something you can actually visualize.
Right, so imagine you're standing outside on a crystal clear night and you shine a flashlight up into the sky. The beam just travels.
Nothing blocks it.
Exactly, nothing blocks it. So in atmospheric terms, that's a low AOD. Anything under 0.1 means very clean, clear air. But if you take that same flashlight and you shine it into this thick, soupy coastal fog, the light just doesn't penetrate.
It scatters.
Yeah, it scatters. It gets absorbed by the water droplets, or it just bounces right back into your eyes.
Right.
That's a high AOD. Yeah. A value above 1.0 means you're dealing with a highly opaque atmosphere.
Like what you'd see if you were standing downwind of a massive forest fire.
Oh, right.
Or, in the middle of a Saharan dust storm. So AOD is literally measuring how much sunlight is being blocked from reaching the ground.
Wow. Okay.
And that light-blocking mechanism is crucial because of how aerosols behave temporally compared to greenhouse gases.
The lifespan difference.
Exactly.
Yeah.
Carbon dioxide is incredibly stable. Once it goes up, it can linger in the atmosphere for centuries.
Centuries.
Yeah, which gives it plenty of time to mix evenly around the globe. It acts like this well-stirred planetary blanket.
Right, okay.
But aerosols are the exact opposite. They have an incredibly short atmospheric lifespan.
The notes say days to maybe a few weeks.
At most. Gravity eventually pulls the larger particles down, or they act as seeds for cloud droplets, and they just get washed out of the sky by rain.
Okay.
So because their lifespan is so short, they just simply do not have the time to spread out evenly across the globe.
They just stay where they are.
Exactly. They pool right over the specific regions where they're emitted, or maybe just slightly downwind.
So you end up with a map of extremes, basically.
You end up with massive spatial gradients. You could have a thick, choking cloud of aerosols over a heavily industrialized river valley, and then completely pristine air over an ocean just like a few thousand miles away.
Wow.
This intense regionality is what makes aerosol loading the odd one out in the planetary boundaries framework.
Which, I mean, that seems like it would create a massive headache for the people trying to set a planetary limit, right?
Right.
Like, if aerosols are pooling in these localized pockets, you can't just take a single global average.
No, you can't.
Because an average AOD would just smooth out all those extreme local spikes, and it'd tell you the planet is fine even if, half a continent is choking on smoke.
Which is exactly why the original planetary boundaries framework back in 2009 couldn't even quantify an aerosol limit.
Really?
Yeah. They knew it was a threat, but they didn't know how to measure a local phenomenon as a global boundary.
That makes sense.
It actually took until the 2023 update for scientists to introduce a workable global control variable, and that is the annual mean interhemispheric difference in AOD.
Okay, so they stopped looking at the global total, and they started looking at the asymmetry between the northern hemisphere and the southern hemisphere.
Right. They realized the danger wasn't just the sheer amount of aerosols, but the
The
imbalance.
imbalance, okay.
Because the vast majority of the world's landmass, population, and industrial activity is located in the northern hemisphere.
Right, right.
Consequently, that is where the vast majority of aerosol emissions happen.
Okay, so I understand that the north is hazier than the south. But I'm kind of struggling with the planetary mechanics here. Like, if the northern hemisphere is hazy and the southern hemisphere is clear, how does that actually destabilize the whole Earth system?
Well, it comes back to your flashlight analogy, but on a planetary scale.
Okay.
So aerosols interact with incoming solar radiation, while some particles, like black carbon, absorb heat. A huge percentage of aerosols, particularly sulfates from burning coal, are highly reflective.
So they act like tiny mirrors.
Exactly. They scatter sunlight back into space.
Yeah.
And when you bounce sunlight back into space before it can hit the ground, you cool the surface below.
Okay, so if the northern hemisphere has a significantly thicker layer of these reflective aerosols, we're basically making the top half of the Earth artificially cooler than the bottom half.
You are fundamentally shifting the Earth's distribution of heating and cooling. And you have to remember, the Earth's atmosphere isn't static.
Right.
It is a connected, fluid dynamic system that distributes heat from the equator to the poles. The biggest weather engines on the planet are driven by those temperature differences.
Ah, okay. The text actually mentions the Intertropical Convergence Zone, the ITCZ.
Right, the ITCC.
Yeah.
It's a massive belt of low pressure and heavy thunderstorms that basically circles the globe near the equator.
And it drives a lot of the world's rain.
It does. It exists because the sun heats the equatorial surface, which causes hot, moist air to rise and dump rain. But the ITCZ doesn't just sit perfectly on the equator. It migrates. It follows the thermal equator, which is the band of the highest surface temperature.
So it follows the heat.
It follows the heat. So if you create a persistent, massive thermal imbalance by artificially cooling the northern hemisphere with a blanket of aerosols.
You alter that thermal gradient.
Exactly. The thermal equator gets pushed southward, away from the cooler northern hemisphere.
Oh, wow.
And when the thermal equator moves, it physically drags these massive rain belts out of their historical positions.
That is wild.
You are altering large-scale atmospheric circulation systems that have been stable for millennia.
But wait, I was looking at the actual numbers in the 2023 update portion of the notes, and I feel like I need to challenge this a bit.
Okay, go for it.
So the text sets the safe planetary boundary limit for this interhemispheric asymmetry at 0.1, right? But the present-day value is listed around 0.076. And furthermore, the more recent planetary health check section indicates that this global imbalance actually got better, like the asymmetry decreased between 2010 and 2024. So if the global number is 0.076, which is well below the 0.1 limit, and the trend is improving, why is the text still sounding the alarm? Like, shouldn't this be a success story? Mission accomplished.
Well, on a purely hemispheric level, the slight improvement is a positive sign.
Okay.
It's largely driven by stricter air quality regulations in places like North America and Europe, reducing their sulfate emissions over the last few decades.
Right, cleaner air in those regions.
Yeah. However, the authors explicitly note that a value of 0.076 is still high enough to fall into a zone of increasing risk and substantial uncertainty.
Okay, so it's not totally safe.
Exactly. But more importantly, relying solely on that global number is incredibly dangerous because it masks ongoing catastrophic regional failures.
Because the averages hide the extremes.
You can have a mathematically safe global imbalance while an entire subcontinent is simultaneously suffocating under a hyperlocalized aerosol plume.
Wow.
The global metric is a symptom of the system, not the entire diagnosis.
That makes total sense. And the notes point directly to where this disconnect, between the global average and the regional reality is hitting hardest, and that's South Asia.
Yes.
The data here is wild. The global asymmetry is sitting at 0.076, but Southern Asia has an annual mean AOD of 0.3 to 0.35.
It's huge.
And the text states the provisional regional boundary for danger is set at 0.25. So South Asia is blowing completely past the regional danger limit, even while the global indicator technically passes the test.
And this is exactly where the theoretical physics of aerosols we were just discussing meets actual human survival. Because the South Asian monsoon isn't just a weather event, it is the lifeblood of the region.
The monsoon mechanics are so fascinating to me. From my understanding, based on the text, it's basically a massive thermodynamic vacuum.
That's a good way to look at it.
During the summer, the landmass of the Indian subcontinent heats up much, much faster than the surrounding Indian Ocean.
Right.
And that hot air over the land rises rapidly, creating a massive low-pressure zone, like a vacuum that physically sucks in massive amounts of cooler, moisture-laden air off the ocean, which then drops as torrential rain.
That is the engine of the monsoon. It relies entirely on the land getting significantly hotter than the ocean.
So applying what we know about aerosols blocking sunlight, throwing a massive smog plume over India, is like, okay, here's where it gets really interesting. It's like trying to boil a massive pot of water to create steam, but right as you turn on the stove, someone slides a giant reflective piece of tinfoil between the flame and the pot.
Yes.
You are blocking the heat source. We are throwing a wrench of smoke and agricultural burning right into the gears of that engine.
That is an excellent way to visualize the disruption. The notes actually detail a severe, complex feedback loop operating over the Indo-Gangetic Plain.
Okay, lay it out for me.
You have millions of farmers engaging in agricultural residue burning to clear fields rapidly between crop rotations.
Which produces staggering amounts of smoke.
Exactly. You combine that with intense fossil fuel emissions from transport and industry, plus residential burning of solid fuels for cooking and heating.
And the winter weather traps it all, doesn't it?
The meteorology plays a huge role, yeah. Cold, stagnant winter air creates temperature inversions that trap all these pollutants near the surface, preventing them from dispersing.
Wow.
So you get this persistent continent-sized shadow of aerosols.
And that shadow acts exactly like the tinfoil.
It physically blocks solar radiation from reaching the surface of the land, preventing the ground from heating up. Simultaneously, certain types of aerosols in that plume, specifically black carbon, absorb solar radiation higher up in the atmosphere.
Oh, so the upper air gets unnaturally warm.
Right, while the surface gets unnaturally cool.
That's completely backwards.
It completely scrambles the vertical heating profile that the monsoon vacuum relies on. If the land doesn't heat up enough relative to the ocean, the vacuum is weakened.
So the moist ocean air isn't drawn inland with the same force.
Exactly.
The text mentions modeling experiments that simulated high interhemispheric aerosol differences, and the results showed an over 20% reduction in mean precipitation over India.
Now, we do have to be careful with models. That specific 20% figure represents a simulated large perturbation, not necessarily a daily weather forecast.
Sure.
But it illustrates the extreme sensitivity of the monsoon system to aerosol loading.
But even if it's a model, if we connect this to the bigger picture, the implications are terrifying. Like, why should we care? A 10% or 20% drop in monsoon rainfall isn't just, a bummer for summer tourism. It's a catastrophic humanitarian crisis.
It really is.
Hundreds of millions of people rely on the precise timing and volume of that specific monsoon for agriculture, for recharging groundwater aquifers, and just for baseline food security. You weaken the vacuum, you starve the crops.
Which really highlights how atmospheric chemistry directly dictates agricultural yields.
Yeah.
But, the threat to human life isn't just about the rain failing. We also have to look at what happens to the people physically standing underneath that plume.
Right.
And this brings us to a crucial distinction in the text between protecting the Earth's climate system and protecting human lungs.
Yes, I was looking at these two metrics in the notes, AOD and PM2.5. And at first, honestly, I assumed they were basically measuring the exact same thing.
A lot of people do.
Because if the air is full of thick smoke, both numbers go up, right? But the text treats them like two completely different types of environmental threats.
They frequently correlate, but they measure entirely different dimensions of the problem.
Okay, untangle them for me.
Think of AOD aerosol optical depth as a vertical measurement taken by a satellite. It is looking down and measuring the entire atmospheric column from the edge of space all the way down to the ground. It tells us the total amount of sunlight being blocked by the entire stack of air. That makes AOD a fantastic Earth system indicator because it tells us about the thermal shading effect that alters monsoons.
But PM 2.5 is completely different.
Very different. PM stands for particulate matter, and 2.5 refers to particles smaller than 2.5 micrometers in diameter.
Which is tiny.
Microscopic. These are fragments of soot, dust, and liquid droplets. They are so small, they bypass the body's natural defense mechanisms.
Oh, man.
They penetrate deep into the lung tissue, and they can even cross over into the bloodstream. PM 2.5 is measured horizontally, directly at the surface. It is a human health indicator measured right at the breathing level.
So AOD is kind of like flying a drone over a swimming pool to see how cloudy the water looks from above.
Felt like that, yeah.
But PM 2.5 is measuring how toxic the water actually is, right where you're actively swimming and accidentally swallowing it.
That captures the distinction perfectly. You can have a high column AOD, maybe due to a layer of dust high up in the stratosphere, without having high PM 2.5 at the surface.
Right.
Conversely, a location can have deeply toxic PM 2.5 exposure for the people living there, without those local emissions being massive enough to trigger a massive spike in the column-integrated AOD.
And this leads to what I think is easily the most disturbing statistic in the entire set of notes.
The exposure levels.
Yeah. It cites literature proposing a safe and just planetary boundary for human health. And they set the safe human PM 2.5 boundary at an annual mean exposure of 15 micrograms per cubic meter. But right now, about 85% of the global population is exposed to levels above that limit.
85% of the human species is breathing air that we know is slowly killing them.
The structural injustice there is just staggering, because a specific region or country can technically have a safe AOD contribution to the global planetary boundary. Like, their total emissions might not be large enough to physically move the Earth's thermal equator or break a monsoon system.
Right. On paper, for the Earth system, they get a passing grade.
Exactly. But simultaneously, their local citizens are suffering immense mortality, asthma, and cardiovascular disease from PM 2.5 exposure. People who contribute the least to industrial emissions often breathe the most concentrated pollution.
And the burden of that exposure is almost never shared equally. The text explicitly points out that the people living near industrial zones or dealing with poor housing quality or occupational exposure, they take the brunt of it.
Yeah.
We have air quality standards on one side and planetary boundaries on the other. They overlap in their focus on aerosols, but they are fundamentally trying to answer two different questions.
Right.
The planetary boundary asks, is the climate circulation stable? The health standard asks, can these people breathe without dying?
Okay, so if we take all of this together, these aerosols are destroying local health with PM 2.5, and they are threatening to break the monsoons and starve millions with high regional AOD. The solution seems incredibly obvious. We need to ban agricultural burning tomorrow, shut down the coal plants, stop driving combustion cars, and just scrub the air clean as fast as humanly possible.
It is the only logical conclusion if you are looking solely at human health and precipitation.
But the source text reveals this massive, deeply counterintuitive catch-22 that I'm still trying to wrap my head around.
It is known in climate science as the cooling paradox or the masking effect.
Okay.
We talked earlier about how certain aerosols, primarily sulfates from burning fossil fuels, are highly reflective.
Right, they scatter sunlight back into space.
By doing so, they exert a negative radiative forcing, meaning they cool the surface of the Earth. Right now, our massive atmospheric aerosol pollution is acting as a global coolant.
Wow.
It is actively masking a significant portion of the global warming caused by greenhouse gases like CO2.
It's like we've unknowingly built a giant, dirty sunshade over the entire planet.
We have.
So if we suddenly do the right thing, if we scrub the air clean to save our lungs and save the monsoon, we rip down that sunshade. And the full blistering heat of the CO2 we've been emitting for 2 centuries just hits us all at once.
That is the exact terrifying reality that knows present. We are trapped in a vice between toxic air on one side and accelerated warming on the other.
So how do policymakers even begin to manage that? It feels like an impossible bind. Like if you put a scrubber on a coal plant smokestack, you filter out the cooling sulfates, which is great for local lungs.
Yeah.
But the plant is still pumping out the invisible warming CO2. You've just cleaned the local air, but accelerated the global warming.
Exactly.
So you have to shut the plant down entirely. But you can't replace a gigawatt of coal power with solar panels overnight. What happens in the gap?
That is the crux of the policy nightmare. This raises an important question. How do societies manage this? The text is adamant on one crucial point.
Okay.
We absolutely cannot use this cooling effect as an excuse to maintain harmful air pollution.
Because of the health toll?
Right. You cannot ethically sacrifice millions of lives to respiratory disease and risk regional famine just to buy a little more time on the climate clock.
Yeah, that makes sense.
The dirty sunshade is not a viable long-term strategy for humanity.
So what is the strategy then?
The notes outline the necessity of what they call a just transition. Policymakers must anticipate this short-term warming spike. We can no longer treat air quality and climate change as two separate departments.
Right. They have to be linked.
We urgently need to link clean air policies, which remove the cooling aerosols, with rapid, aggressive decarbonization, which removes the warming greenhouse gases. If you completely phase out the burning of fossil fuels, you tackle both the CO2 and the sulfate aerosols simultaneously.
But there's still a lag, right?
Yeah.
Even if we magically shut off all fossil fuels tomorrow, we already established that aerosols fall out of the sky in a matter of days or weeks.
Yes.
But the CO2 we've already emitted is going to stay up there for centuries. So the sunshade disappears instantly, but the warming blanket lingers.
Yes, there will be a near-term warming bump. The climate response will be nonlinear. Unmasking that warming is going to put immense stress on ecosystems and human infrastructure, but it is the only physical path available to eventually stabilize the Earth system and protect human health. Managing that transition requires institutional coordination that is, frankly, unprecedented.
I can't even imagine.
You need air quality agencies, climate scientists, agricultural departments, energy grids, and urban planners all sharing data and acting together, understanding that a policy that fixes one problem might temporarily exacerbate another.
It is a phenomenal, terrifying synthesis of how interconnected and fragile this whole Earth system truly is.
Yeah.
Let me just quickly recap the ground we've covered today.
Go for it.
We're basically dealing with three distinct but completely overlapping layers of crisis. At the local surface layer, you have PM 2.5 destroying human lungs and creating a massive environmental justice crisis.
Right.
Then at the regional layer, you have thick, light-blocking aerosol plumes threatening to disrupt the thermodynamic vacuum of the monsoons, which feed hundreds of millions of people.
Yeah.
And finally, at the global layer, you have the interhemispheric asymmetry in AOD, that global tug-of-war, threatening to shift planetary circulation systems like the ITCZ.
And this layered framework is a perfect example of why critical thinking is required in modern science. It proves why we can't accept superficial environmental metrics.
Right.
You cannot just read a headline that says, global aerosol boundary is safely below 0.1, assume the sky is fine. You have to interrogate the data.
You have to ask, who is being averaged out?
Exactly. Who's being averaged out to make that number look safe? Whose lungs are absorbing the pollution so the global mean stays low? Knowledge is only valuable when it's understood in its full, complex context.
There's one specific thing from the notes I haven't been able to stop thinking about since we started prepping for this deep dive.
Oh, yeah. What's that?
Well, we spent this entire time talking about human pollution, right?
Mm-hmm.
Coal plants, agriculture, fossil fuels. Things we can theoretically control with the right policies.
It's a theory, yeah.
But the text explicitly mentions that massive natural events, like a major volcanic eruption, can inject enough aerosols into one hemisphere to shift monsoon rainfall thousands of miles away. It cites historical droughts in the Sahel caused by natural aerosol forcing.
The natural aerosols that we have absolutely no control over.
Exactly. And the text also notes that climate change is actively altering the frequency of natural wildfire and dust emissions. So it makes you wonder, what happens if human-driven climate change triggers a permanent increase in massive natural wildfires or mega-drought dust storms, but concentrated heavily in just one hemisphere?
Oh, wow.
We could do everything right. We could execute the perfect just transition, shut down the coal plants, fix all our human pollution, and still find ourselves locked into a permanent natural hemispheric tug-of-war triggered by the warming we already baked into the system.
That is a chilling thought.
We might just hand the reins over to a feedback loop we no longer have the policy tools to control. It is definitely something to chew on the next time you're admiring a deeply red, hazy sunset.